All right, welcome back. We're almost there. So you can see the yellow highlights. We've covered a lot of material. We're on to the green highlight now, solving uniform velocity and uniform acceleration problems using algebraic methods. So today we're going to look at something called the Big Five. Okay, oops, jumped too far ahead. So we're going to look at solving problems with 5 kinematic equations. Okay, so kinematic, remember, is the study of motion, and there'll be 5 equations that we're going to use. We'll develop 3 of them, and then the other 2 sort of fall into place. So let's start. We have a nice little velocity time graph here. Okay, so we're going to use this to develop our first equation. So we have a VF, which stands for V final. So this is final. We have a VI, which stands for initial or start. Okay, and we're going to find the area under this curve, okay, or graph. So I've chopped it up into two parts. There's a triangular part and there's a little rectangular part on the bottom. This length right here is VF minus VI. It is the difference between the highest value and the initial value that we started with right here, not the 0. Okay, so when we go to look at this triangle, we're going to have delta t as a base. We're going to have VF minus VI as my height. And so when we go to find area 1, it's going to look like this. 1/2 base times height. This is area number 1 right here. This is area number 2. Okay, so you have a triangle plus a rectangle. Okay, so there is 1/2 base times height. So the VF minus VI, this is the height if you want to think of that as the triangle. And then this over here, this is the rectangle. Delta t times this height right here is just VI. So take a minute, pause it, study that. It's not as complicated as it looks, but because there's no numbers, it's sometimes distribute, or we multiply out to get rid of that bracket. So you're distributing this term into here. You'll notice that 2 of the terms now have 1/2 delta t. And then we should notice that of those terms, you have a VF delta t and a VI delta t. Well, this one here and this one here are like terms. Okay, so they can actually be combined. So just like in math class, we can bring those two together, and they turn into a positive 1/2 VI delta t. Now, if you look at this one, you'll notice a couple pieces. They both have halves in them. They both have delta t's in them. Okay, and so what we could do is we factor, everyone's favorite math word. We factor out the 1/2, okay, and the delta t, and we can either write it out front or you can write it this way. So either way, you could have this like this. Those would be the same. What we're going to focus on though is this is equation 1. Okay, so the area under a velocity time graph is the change in position, our displacement right there. Okay, so by finding the area under this graph, you have found the change in position, the displacement. And here's a handy formula which allows you to find that change based on only knowing the initial, final velocities and the change in time in which it took place. Okay, there's equation 1. Let's do it this way. We'll hide some of this so it's not overwhelming. So we also have this equation for acceleration. So our average acceleration right here, you'll recognize that as a slope formula. So if we rearrange that to get VF by itself, okay, so this is just a rearranged slope formula, you now have equation number 2. Okay, so we have 2 equations developed out of our 5. To get the third equation, okay, we're going to take some information from equation number 1 and we're going to substitute it into equation number 2. So we'll start with equation 2. We're going to isolate or highlight, we're going to isolate the VF from equation number 1. Okay, so we rearrange that equation and then we sub equation, we're going to sub equation 2 into equation 1. I've got to make sure I get my order right here. So this VF right here, is going into equation 1. Okay, so you can see the VF is replaced by this element right here, which is this piece right here. So I think I said that backwards. We're putting equation 2 into equation 1. So just for clarity, you're not responsible for the proof of this in any way, shape, or form. But by the time you manipulate, clean up the algebra, and collect like terms, you end up with our third equation, which is this guy right here. Okay. Now, I think the fourth one and the fifth one are left for you in your homework. The proofs are very similar. You're not responsible for them. They're just kind of fun to explore. But these are your 5 kinematic equations. Okay, and they are located on page 37 in your textbook. These are always provided. You do not have to memorize these ever. Okay, having said that, after you've done enough problems, you will start to recognize them and you'll be able to pull them into your solutions without actually looking at this table. So the value of these 5 equations is it allows us to solve for missing elements in the problems without having to draw all the graphs and things. Someone simplified it down into these equations. So if you are given this information, then you should be able to solve whichever equation you're working on. This is the missing piece, so that is how you can exclude various equations. So let's have a look. Once we do a question or two, you'll see how this works. So here we go. A sports car approaches a highway on-ramp at a velocity of 20 meters per second to the east. If the car accelerates at a rate of 3.2 meters per second squared to the east for 5 seconds, what is the displacement of the car? So let's start with what is given. Okay, well, we're given a velocity, and it's an initial velocity. So we'll write that down as 20 meters per second to the east. We're given an acceleration, and we know that because this is squared. It's 3.2 meters per second squared, again, to the east. We are given a time value, 5 seconds, and we are asked to find the displacement. Okay, so we're looking for d. So those are what we're trying to find. So now when we go back, and you can flip back here to the equations, we're looking for an equation that has those 4 variables in it. Okay, so a vi, an a t, and a d. So you'll notice the things we don't have are a vf. Okay, so if you look over here, this is the equation, a variable not in the equation. We don't have VF. We have all of these pieces. So this equation right here will probably work for us. And we'll go and try it. Now you'll notice I don't write the deltas. It just gets a bit cumbersome when you're trying to write all that down. So we would have D equals VIT plus 1/2 AT squared. That will be my equation. And if you go through and you double check, this is what we're looking for. We know this, this is a constant, we know A, and we know T. We should be able to solve this problem for D. Okay, so now let's try it. D equals. The other thing I'm also checking at this point in time are all my units in the correct meters per second, meters per second squared. I want to make sure all of those are aligned as well. That's a really important step, and we'll focus on that shortly. So then I fill in what I don't know and what I do know, and I get something that looks like that. Okay, so I know all of those variables on the right-hand side of the equation. I grab my calculator. First one's 100. That's pretty straightforward. 25 times 3.2 times 0.5, and then I get plus 40, and I would finish up with 140 meters to the east. Okay, because that is the direction we were traveling, and that's all there is to it. So the couple steps that I'm looking for, I want to see you list what's given. That's really important for me. Okay, I want to see the equation. Okay, that's a really important piece as well. And then this piece right here, okay, if you do show some work, that makes it a lot easier for me to help determine where you're making mistakes. It also communicates your vast knowledge of the topic. So those are the three pieces that are going to be in every question. Okay, and then if you wanted to, you could finish with therefore the displacement is 140 meters to the east. Okay, and that would be a complete question. So let's try another one. A sailboat accelerates uniformly from 6 meters per second. So when I do these, I like to write things down as I go. There's VI. To 8 meters per second, there's VF. At a rate of 0.5 meters per second squared, there's an acceleration. What distance does the boat travel? So I'm looking for a D. So if I'm going to write all of this down, I've got VI is 6 meters per second. VF is 8 meters per second. Acceleration is 0.5 meters per second squared. So far everything is in meters and seconds. That's awesome. And we're trying to find a D. So there, I fulfilled obligation number 1. Obligation number 2, write the equation. So I need to find an equation that ties all of those together. Okay, so if I backtrack 2 pages here, we should find equation 4. If you'll notice, has VFs, VIs, accelerations, and Ds, which is what we're looking for. Okay, so we have VF squared equals VI squared plus 2AD. And if we do a quick check to make sure we have this information, we have VI, 2 is constant, we have A, but we don't have D. So we may have to do a little bit of algebra manipulation to solve this. So 8 squared equals 6 squared plus 2 times 0.5 times D. Okay, so this is 64, this is 36, 2 times a half is just 1, so this just becomes a D. And then if we subtract 36 from 64, we get our 28 meters, and it has a direction of to the north because everything was moving in the same direction. Now when those start to change to be opposite directions, we'll have some other issues to deal with, but for now we're happy with this. So therefore displacement is 28 meters to the north. Okay, so I've got my equation, I've got my givens, I've got my work, and I have my concluding statement. That's a nicely laid out question. All right, let's try another one here. A dart is thrown at a target that is supported by a wooden backstop. It strikes the backstop with an initial velocity of 5 meters per second. So there's VI. The dart comes to rest in a very small time element. Okay. Here's the first problem. A dart is thrown at a target that is supported by a wooden backstop. Okay, just setting the scene. It strikes the backstop with an initial velocity. The dart comes to rest. Now there's some hidden information here. Rest means VF equals 0. Okay, so we have to learn to extract that information. We're looking for acceleration, so if we go through our givens, we have VI equals 5 meters per second. VF equals 0 meters per second. Time is really small, and we are looking for acceleration. Without doing any work whatsoever, we should anticipate that that acceleration should be some negative value. Okay, we're not going to use that in our calculations. We'll let the calculation do all the work for us. But we would expect or anticipate that the acceleration value should be negative because it needs to slow this object down. So we've done what's given. Now we need to find an equation. So something that has VI, VF, T, and solves for an A. So if we jump back here, I'm thinking, well, if we look at this one, we didn't have any D information, so we can't use equation 1. But if we look at equation 2, we had VF, we had VI, we had T, and we were looking for A. So I would use equation number 2. Let's go write that down. So equation number 2, VF equals VI plus AT. And now we substitute in our information. So 0, 5 plus A, 0.050. Make sure I get that right. Okay, so now if we want to rearrange, we subtract 5 from both sides. There we go, 0.050 times a. Divide both sides by 0.050. And we end up with a equals, and I don't know that one off the top of my head. Should, there we are, duh. 100 meters per second squared, and it would be negative. Now, it's negative. We anticipated that already because it has to be an acceleration in the opposite direction of the velocity, otherwise it's not going to slow this object down. And now 100 meters per second squared, that seems like a really big number. If the dart was traveling for 1 second with this acceleration, it would be going 100 meters per second, which would be a really dangerous dart. But it's only actually accelerating at negative 100 meters per second squared for a very short time period, and that's what can sometimes be a bit confusing when you're looking for values of acceleration. Okay, so you have to kind of think of them in context of the problem. Don't just look at the number and go, whoa, that's super big. All right, so there's 2 for you to try. We have a football player and a child on a toboggan, so pause it here, and then I'll go through them really quickly. Okay, so a football player initially at rest. There's that hidden information. VI is 0. Okay, accelerates uniformly as she runs down the field, traveling 17 meters, so there's a D, in 3.8 seconds. There's a T. What is her final velocity? So that's what we're looking for. Okay, so we have D is 17 meters, T is 3.8 seconds. Might be a bit lazy just because I don't have a lot of space here. So I need an expression that lets me solve for VF. All right, so if we go through our equations, I don't have time. I do have time. I don't have A. So let's go back and have a look. What are we missing? We're missing A. So if we're missing A, then this expression right here, okay, the average should get me to my answer. Okay, where am I? There I am. Okay, so D equals VF plus VI over 2 times T. D is, gotta get out of the way of my own projection here. There we are, 0 over 2 times 3.8. So 8.5 times 3.8. And we get 32.3 meters. And it should be to the east. Let's take a look. Oh, I found the wrong thing. That was silly of me. Her final velocity. Oh, see, this is what happens. I put things in the wrong spot. Okay. Now, if you were to do this, say on a test or something, have you written down your variables? Yes. Have you written down the correct equation? Yes. Did you simply just put something in the wrong location? Yeah. So I can give you a good chunk of the marks for this. Okay. Because you've clearly picked off some of the important information. However, what I needed to do, let's go back here, I need to put the information in the right location. That's a pretty big issue. So here we go. Let's go back and find VF plus 0. That's a little better. And then this is 3.8. Okay, so then this would be 34 equals 3.8 VF. That's looking better. So now we divide that out. Happens to everybody. 8.9 meters per second is VF. That looks a little bit better. Okay, so mistakes happen. Just show your work. We can talk about it. That's how we learn. A child on a toboggan sits at rest on the top of the tobogganing hill. If the child travels 70 meters, so there's D, 5.3 seconds, there's T, accelerating uniformly. What acceleration does the child experience? So they're at rest, so VI equals 0. Okay, so let's list what we have. 70 meters, 5.3 seconds. We're trying to find A. I like to write that down, even though I ignored it the last question. Whoops. And we have 0. So I think we can use equation number 3 will probably work. Let's take a quick look. So let's go through, and what do we actually have? We know D, we know T, we know VI, we're looking for A, we know T. This equation should work. Okay, so let's give ourselves a little more room to write. We have 70 meters. This first term will go to 0 because VI is 0. We have 1/2. We want A, and we're going to put in 5.3 squared. Okay, so now we just follow our bedmass rules, do our exponents first. 5.3 times 5.3 divided by 2. Then this becomes 14.05a. Divide both sides by 14. We get about, let's just say 5. It's probably easier. So 5 meters per second squared should be our acceleration. And it's going downhill. I should add the direction. Okay, so sorry about the mistake, but you know what? It happens. We learn from it. That's why we do the process. Questions to try. Page 39, 1 to 3, 5, and 6. Thanks for tuning in.